Hello YouTube. So in this second lecture, we'll be covering another technique for evaluating differential equations. We'll be covering something known as a separation of variables. Now the separation of variables can be used for a lot of different equations. It's just limited to a certain case where we'll have, for example, I'll just have two variables, x and y. X is the independent, y is the dependent. And we could separate whatever's on this right side into two different functions that are a product of two different functions, f of x and g of y. So, for example, let's say we have dy over dx equals x squared times y. We can separate this into two different functions. So we can have f of x equal x squared, g of y equal y. So we can separate it like this. So the method that we'll be covering is as follows. So we already have our dy over dx equals f of x over g of y. So this is our first step, separating our initial differential equation into this. So our second step is to divide both sides by g of y. So now we have 1 over g of y times dy dx equals f of x. Now we can multiply both sides by dx. So we now have dy over g of y equals f of x dx. Then we can integrate both sides. And then from here you can solve for y using some algebra, but since this is just showing you the method, I can't really go much farther since we don't know what f of x and g of y is. So let me give an example. So let's say we have dy for dx equal x squared plus 1 times y squared plus 1. Okay? It's separable because, well, this is our f of x, this is our g of y. So it's separable. It's the product of f of x and g of y. So this is our step 1. Now, step 2 is dividing both sides by y squared plus 1 because we divide by g of y. So we have dy dx times 1 over y squared plus 1 equals x squared plus 1. Now we can multiply both sides by dx. So now we have dy over y squared plus 1 equals x squared plus 1 dx. Okay, so we're already here. We're at step 4 now. Now we integrate both sides. That gives us, not ln, inverse tangent of y plus c1 equals 1/3 x cubed plus x plus c2. And since constants are really arbitrary, you can just bring this c1 to this side. So we just subtract both sides by c1 to end up with this constant on this side. So now we can just put this here. Okay, so now we could just take the tangent of everything. So that leaves us with tangent of, okay, let me just have okay handwriting first of all. Tangent of 1/3 x cubed plus x plus c. This is the general solution. We can get a specific solution if we have the initial values. But since we're not given any values or initial values, this is going to be our solution since we don't know what c is. Okay, so now you know how to use separation of variables. Let me give you an example. Let me just erase this here. Let me erase this too, so you don't. Okay. If you want to go back in the video, you could do that if you want. So let's say we have dy over dx equal to e to the x plus y power. And you could initially look at this and be like, wow, this looks hard. Trust me, it's really not. You can separate it in terms of f of x and g of y pretty easily. So to begin with this problem, you could say dy dx e to the x plus y can be separated into e to the x times e to the y. So we already have our f of x and g of y. Okay, so now we could divide both sides by e to the y. So now we have 1 over e to the y dy over dx equals e to the x. Now we can multiply both sides by dx. So we now have dy over e to the y equals e to the x dx. Now we can integrate both sides. So we can have integral of e to the negative y dy. We're just using algebra here because anything in the denominator is just that to the negative first power. Integral of e to the x dx. Then we can say this is negative e to the negative y equals e to the x plus c, where we had a c1 here initially, but we just transferred it over to this side, just like we did in the last problem. So after that, solving for y is just simple algebra. So let me just finish the algebra. So we could make both sides negative, so we now have e to the negative y equals negative e to the x plus c. C doesn't really, I don't really have to change how c looks because it's an arbitrary constant, so whatever c, the only thing about c that matters is that what it is in the end. So what c looks like here doesn't matter because it's just an intermediate calculation. You could solve for c once you evaluate everything. So take the ln of everything. So we now have negative y equals ln of negative e to the x plus c. And then you could take the negative of everything. So y equals negative ln of negative e to the x plus c. That is our final solution. And we could probably verify by plugging this into here, but I'll just leave that as an exercise for you. Because I'm just lazy and I don't want to have to do that. Anyways, thank you for watching this video, and I'll see you in my next video.